All right, having talked about z-intervals and t-intervals so far, we're about to move on to one more kind of confidence interval, which are confidence intervals for population proportions. So before we jump into that, let's talk about what a population proportion is. Realistically, a population proportion is pretty much a percent. So for example, if we have a simple random sample of n individuals, okay, so maybe that's 5, and we're going to let x be the number of the people in the sample who have a characteristic that we're studying. And so that number will be x. And then the sample proportion is what we have listed right here, which is p hat equals x over n. Yeah, so this funny looking triangle thing, that thing is actually, and just to kind of write this a little bit bigger so you can see what's going on, the way that we pronounce that is p hat. Okay, that is not a joke. That's true, p hat. So that's how we read that. P hat equals x over n. So a really quick example of where you may have seen this before. Maybe you've seen the old Trident commercials where it said 4 out of 5 dentists recommend, recommend Trident to fight cavities. Now, first off, I hope that by now in this class you're starting to question statements like that. 4 out of 5 dentists recommend, like which 4 out of which 5? What are we talking about here? What sampling method was used? Pretty sure it wasn't simple random sampling. But if we were to use that, if we were to assume it was, or just for the purposes of this example, x is the number that recommend Trident, okay, which would be 4 out of 5, the total number of individuals in our sample. And so 4 out of 5 would give me a p hat value, okay, a sample proportion of 80%, 0.80. So that's the kind of thing we're talking about here. Pretty straightforward. 4 out of 5, that's a sample proportion. It's certainly not a simple random sample proportion, but it is a sample proportion of sorts. Now, for just a little bit more notation here, here's what we've got. The population proportion is just represented by p, no hat, but the sample proportion is represented by p hat. And often, for our purposes, we're going to be using p hat, this sample proportion, to estimate the population proportion p. So when you see a p by itself, we're talking about the whole population, but when you see the p hat, that's when we're talking about the sample. Now, for just a very simple example of using this sort of idea, if we had 108 families who were sampled to see if they had a microwave, and 102 responded yes, okay, we're asked to find the sample proportion here. And so, simply enough, what we would do to find p hat is we would write this as 102 out of 108. And when I put that into my calculator, I find a value of 0.944, and that ends up being 4 repeating. And so what we can say, if we were to use this point estimate that we have here, 102 over 108, as an estimate for the population, we would estimate that 94% of the population had a microwave. So what we're using here is, this is probably not new mathematics to you, but it's new to our class in the sense that we have been computing using means as point estimates so far, and we can actually use proportions as point estimates as well. Now, this section is on confidence intervals, and remember, everything we've done so far with confidence intervals has been based on the fact that sampling distributions are normally distributed. And so if we know we've got something that's normally distributed, or at least approximately normally distributed, then we can use that fact to create this confidence interval. Well, we don't have any fact like that for proportions, but it turns out that just like we had the central limit theorem, remember the Penny Lab, for means and for samples, in that sense, there's also a central limit theorem for proportions. And it's stated right here. Remember in the central limit theorem, we said that we had to have a population that was size 30, bigger than 30. Well, that part of this for proportions is right here. That in P and in 1 minus P, okay, and notice this is just the complement. So the number of people who are in one category here, the number of people in the success category, and the number of people in the failure category, both of those have to be greater than 10. So we can kind of simplify that by saying we have to have at least 10 people in each category. So for example, in the microwave example, we had 102 in the success category, 102 people who had microwaves, but we only had 6 families who didn't have a microwave. And this wouldn't meet this criteria. This one certainly would. We have more than 10. But as far as the people who don't have microwaves, that wouldn't mean that criteria of being at least 10. And so this is the sort of thing that we have to look for. Instead of a sample of size greater than 30, we have to make sure we've got at least 10 on each side. Now, provided that happens, then the central limit theorem for proportions says the distribution of p hat, the sample proportion, is normally distributed with a mean given just by the proportion itself, the actual population, just like we said that the mean is the mean of the population, and with a standard error of the mean, okay, so similar to how we calculated standard deviation before, of radical p times 1 minus p over n. And so this is the central limit theorem for proportions. This concept is the concept that allows us to make confidence intervals for proportions. Now we've kind of gotten the hang of confidence intervals and we know we can do this with the calculator. So let's jump straight into the assumptions we need. Number one, not surprising, we have to have a simple random sample. So this is one of the assumptions to make a confidence interval using sample proportions to estimate the population proportion. So simple random sample. 2, the population is at least 20 times as large as the sample. You may remember from earlier in the course that we talked about that if this happens, then we can assume that our sample is independent. And if it doesn't, we can't make that assumption. So that's why we have that second criterion here, that the population is at least 20 times as large as the sample. Number 3, the items in the population are divided into 2 categories. So this kind of has a binomial feel to it. And think of the example we just had with the microwaves and no microwaves. That's what we're talking about. Either, we have to be able to break it down into kind of a 2-situation system here where we have either somebody has a microwave or they don't. And then number 4, which we just talked about, is the assumption in the central limit theorem for proportions, is that the sample has to have at least 10 individuals in each category. So that's why the microwave example, we actually couldn't have used that to generate a confidence interval, because we only had 6 in the no microwave category. We have to have at least 10 in each category. Now, we're not really going to use this procedure by hand to construct a confidence interval, but I do want to call your attention here to step 4 and just say, if we were creating a confidence interval, notice we're basically doing the same thing. We had in previous sections, we had x bar plus or minus z sub alpha over 2 times sigma over radical n. And so we have the same thing here, except for that instead of a sample mean, we've got a sample proportion, okay, plus or minus, still z sub alpha over 2. And remember, this was our standard deviation, our standard error in the mean in that box above when we were talking about the central limit theorem. And so I just wanted to point out that this is really the same process, using a different calculation for standard deviation, but otherwise it's the same sort of idea that we have been using in the previous 2 sections. Okay, now here we have just a statement that 35% of adults in America eat pizza at least once a week, and then a random sample of 250 adults in a medium-sized college town were surveyed, and it was found that 110 of them eat pizza every week, at least once a week. And we're to use this data, and by this data we're talking about the sample data here, to estimate the true proportion of Americans who eat pizza at least one time per week with 90% confidence. So let's go ahead and jump over to the calculator. We're going to go into stats again. We're going to go over to tests like we do with all confidence intervals. And what we want is we want a 1 proportion z interval. So I'm going to go ahead and scroll down. So here's the z interval, here's the t interval. And as we continue to go down, we've got some other intervals that we haven't used yet, but we'll learn. Okay, the clue here is that we're talking about population proportions. So we want the 1 proportion z interval. Okay, not 2 because we only have 1 proportion at this point. We'll get into 2 proportion tests later. But 1 proportion z interval. Now note that there's no t interval for proportions. It's only a z interval, so you don't have to worry about that. 1 proportion z interval. It asks me for my x value, which in this case was 110 out of 250. Okay, our confidence level is 90%, so I'll put 0.9 or 0.90, and then calculate. And this is the value that I get when I calculate. Let's go ahead and put that in the notes. Alright, so I'm just copying that interval over, and I got 0.38836 to 0.49164. This is not part of the interval, but I'm just kind of writing it because my calculator gave me that 0.44. Okay, so that tells me that in this sample, the proportion of college students who eat pizza at least once a week is 44%. In part B asks us, do we consider this to be a representative sample for the true proportion of American adults who eat pizza at least once a week? Well, we were told here at the beginning of the problem that 35% of adults in America eat pizza once per week. So that's for all of America. Now we're taking this very specific view of a college town, students or adults in a college town, and we got this proportion that's higher than 35%. And even more telling is this, that if we look at that 0.35 we were given, it does not lie within the interval. It is not in the interval. So what that tells me is this sample is not representative of the true proportion of Americans who eat pizza once per week. The 35% is not the only thing that I needed to know it wasn't representative. First off, we were talking about a medium-sized college town. And I wouldn't expect the eating habits of college students, especially in like a college town, to be representative of the whole population. So we can just answer this with a simple no. And our reasoning is the fact that we've got this 0.35 for all Americans that doesn't fit in the confidence interval. Now for part C here, we're asked to keep in mind our answer to part B, that this is not representative of all Americans, to interpret the confidence interval. So we're going to say, as usual, we can be 90% confident. Now at this point, I'm looking back up to the problem. I want to be precise. So who was surveyed? What is this based off of? I'm going to say we can be 90% confident that adults in the medium-sized college town that were surveyed, okay, or rather adults who lived in the town where this survey took place, eat pizza between 38.8 and 49.2% of the time. Okay, so we'll kind of clean that up here. Okay, so I have to make sure in my answer here that I specify who we're talking about, adults in the college town that was mentioned, okay, and then I'm just reading from the question, who eat pizza at least once per week is between 39 and 49%. We don't want to extrapolate this to all college towns, or certainly to all adults in the United States. We can only really extend our findings to the college town that was surveyed. And so I'm just trying to be careful here with what I've highlighted to mention that those are the people that our results are being applied to. All right, here we've got another problem. Studies performed to determine the percentage of the nation's 10 million asthmatics who are allergic to sulfites. And in this survey, 38 of 500 randomly selected asthmatics were found to be allergic to sulfites. So one thing that we have to keep in mind, and kind of I've been doing this but not explicitly, is are our assumptions being met? Do we have a simple random sample? Is the population very large? Okay, we've got 10 million asthmatics, so certainly 500 asthmatics is not 20%, or rather is not 5% of the population. Or in other words, the population is definitely 20 times larger than our sample group here. All right, we do have 10 in each category. We have 38 who are allergic to sulfites, and then 462, if we find the complement of that, who are not allergic to sulfites. So we've got at least 10 in each category. Now, we definitely have a population proportion, 38 out of 500. So let's come over to run a 1 proportion z interval. So I'm going to go ahead and scroll down to 1 proportion z interval. And in this case, my x value is 38. And n is the total of 500. And here we're asked for a 95% confidence interval. So we just input that information into the calculator. And as we do that, we get this interval between 5.3 and 9.9%. So we can come back and answer the question and jot this down and then interpret our interval. All right, so at this point I can just copy down what I have on the calculator, which was these values between 0.05277 and 0.09923. And if I were to interpret this, I would say we can be 95% confident that between 5.3% and 9.9% of all U.S. asthmatics are allergic to sulfites. Okay, so again, we start with that kind of statement that we use every time. The 95%, we can be 95% confident in that. And then I look at the problem to make sure that I'm using the information here correctly. And I'm being specific about the population that we can infer this of, considering the fact that that was the population that was surveyed. Now, part C asks us to determine the margin of error for the estimate of P. And I'd just like to remind you that that margin of error is always one of two things. We can say it's either the distance from P hat to either one of these values on the interval, or we can just take half of the width of the confidence interval. And so to me, to answer part C, the easiest thing to do here would be to take 0.09923, okay, the upper end here, subtract the lower end of our interval here, and then I want to divide that by 2 because remember this is the plus or minus. So the whole interval is kind of, that's not my margin of error. My margin of error is from the middle of that interval in either direction. So go ahead and divide that by 2, and that gives us a value of 0.02323. Okay, so actually I got that number using the confidence interval above. And so that's my margin of error for P hat. Note that that's very similar to what we did in earlier sections to find the margin of error. We either found the point estimate and subtracted the high end from that, or subtracted the low end from that, or we said we could just take the whole interval and then cut it in half, and that'll give me the margin of error. Now you may remember that was only one way that we found the margin of error. We also had a formula to find the margin of error, and we have a formula to find the margin of error with proportions as well. Now for proportions, it turns out that we have two formulas to find the margin of error. Remember, we just did kind of an algebraic calculation using the margin of error earlier to find a formula that looked something like this, where we squared to figure out what the margin of error is. Here we have two options. If we have a p-hat value, if we have a sample proportion, then we can use the numbers from the sample proportion to estimate the sample size we need for any particular margin of error. Okay. Now, if we don't have a value for p-hat, no value for p-hat is available, so we don't have a sample proportion, then we can go ahead and use this formula. This formula, what it does is actually maximizes the error and says this would be the maximum error. It turns out that that maximum error would happen if the proportion was at 0.5. And so we just assume that we've got 0.5 success and failure. And if we do that, then it'll give us the maximum error, which will be a little bit more than what this tells us, a little bit higher, I should say, than what this would give us. But if we don't have data available, we have to go with that. So here we have one last example where we're going to look at using these margins of error to estimate what sample size we would need. And so we've got a medical researcher who wants to construct a 99% confidence interval for the proportion of knee replacement surgeries that result in complications. Okay, we've got first some data that says an article suggested that 8% of operations result in complications. So if we were to use that 8% as an estimate, the question is what sample size would we need so that the confidence interval will have a margin of error of 0.04. All right, now the first thing we're going to need to do is think about what value do we get for z sub alpha over 2. And so remember, if we just sketch a normal curve here, and 99% confidence interval means that the vast majority of the data is going to be kind of included in the middle here. And what we need for our z sub alpha over 2, remember this is just a z-score. I just want to find out what's that z-score. If it was 99.7, I know it would be exactly 3. So it's going to be 2 point something. Remember, the way we do this with the calculator is we have to look at this and say, well, that then is 0.5%. Okay, and the reason that that's 0.5% is because together these two tails have to come out to be 1 full percent. So I know each one is 0.5%. In fact, let me actually write 0.5% here. 0.005. Okay, 0.5%. 0.005. So each one of these is 0.5%. And from there, I can use the inverse norm function on the calculator. Remember, if this is 0.5%, then what's left to the left would be 1 minus 0.005, which is 0.995. Okay, and so this is the value I'm going to want to insert into my calculator. Okay, so remember, I'm going to have to go into distributions to find inverse norm. And I'm assuming that your calculator does not have this update, so it will by default give me the left. And I need to put in 0.995, the complement of 0.005. That will tell me the z-score to the left. Okay, when we're finding z-score, we just can leave it between 0 and 1 here. And so I'll go ahead and paste that, and I get a z-score of 2.58, which is kind of what we had expected earlier. Okay, so that work was just to determine here that z sub alpha over 2 is equal to 2.5758. Leave this, out a couple of a few extra decimal places to make sure I get an accurate estimate. And so now I'll just use those formulas. Now, if we're assuming that we have a value here, an estimate for p hat, then the formula I want to use is n equals, p hat 1 minus p hat, and then that is z sub alpha over 2 over e squared. Okay, just the formula from the previous slide. And now I'll just plug those values in. So if p hat is 0.08, right, 1 minus p hat is the complement, 0.092. and then I'll take z sub alpha over 2, which we got as 2.5758, and over my margin of error, which is 0.04, and it's just this second quantity that I'm going to square. And the value that I get when I do that is 305.20 basically. But we know that if I want this to be within that margin of error, we always have to round up. And so that would give me a value of 306. Okay, so that was just putting these things into the calculator. Remember, we're only squaring the second set of parentheses. And if I do that, I get 305.198, rounds up to 306. Now, if we don't have an estimate for p, in that case we have to use this other formula. There's 0.025, but it was the same information here, z sub alpha over 2 divided by the margin of error squared. Okay, and so if I do that, I get 0.025, and then the same thing that I've got from this set of parentheses, 2.5758 over 0.04. Okay, so this was assuming if we didn't know what p was, if we didn't have an estimate for p, then this is what we would have to plug in. And let's see what we would end up getting here. So I'm putting that into my calculator, and when I put that into my calculator, I get n equals 1036.679. Okay, the n is 1037. Okay, and that's my sample size. Now, just before we end, I want to compare these two numbers. Why is there such a huge difference? Well, what I'd mentioned earlier is that this number right here is assuming the maximum error. If we don't have exact, an estimate to go off of, then we have to assume the max, and that means it's going to give us a larger sample size than we possibly need. Okay, it assumes it's kind of erring on the side of caution, so we get a much larger sample size than we need, given the true population, proportion or the estimate of that. And so this will be a more accurate value, and it will be a smaller value in general. It will always be smaller or equal to the maximum value using the second formula. And but if we don't have that population proportion to estimate from, okay, then we have to use the second formula, and it will of necessity give us a bigger value. If you're wondering, is there an easier way to do this on the calculator? The answer is no. There's no button that does this this estimate on the calculator. We have to go ahead and find the sample size ourselves. So those are a couple formulas that we'll have. I will tell you this. I would be giving you those formulas on the test if I expected you to be using them on the test. So no worries from that point of view. And that's it for population proportions and confidence intervals.